In a physical system, transport phenomena is an important feature to be studied. In kinetic theory, which will be introduced further in this lesson, Knudsen number helps to determine whether statistical mechanics or the continuum mechanics formulation of fluid dynamics should be used to model a situation. The Knudsen number is defined as the particle mean free path divided by the flow length scale. The mean free path is a measure of the mean traveling distance of a moving particle before it hits another one. In the right figure, when particles collide very often and their mean free paths are much shorter than the obstacle, the fluid can be seen as in local equilibrium and the flow is a continuum flow. In this case, the atomic scale molecular dynamics, microscale direct simulation Monte Carlo and lattice-Boltzmann method, and the macroscopic CFD with Navier-Stokes equation can all be used to model the flow. When the mean free path is similar or longer than the flow length scale, the flow is a non-equilibrium flow and continuum laws break down. In this case, we need to use discrete models to deal with the flow problem. Molecular dynamics is certainly a powerful tool to study non-equilibrium flow. However, its huge computing load limits its application in relatively larger systems, such as a micrometer level channel flow. Here we introduce an alternative called direct simulation Monte Carlo, abbreviated as DSMC. It is faster than MD because it uses hypothetical particles. Each particle in DSMC represents n number of particles in the system. In this way, the degrees of freedom in the system is greatly reduced. In contrast to MD, DSMC uses a probabilistic approach to sample the collisions. The interactions included in DSMC are external field, such as gravity, pair interaction for pair collisions, and boundary conditions. DSMC can be applied to many non-equilibrium flow situations in microfluidics, chip cooling, and flow in porous materials. DSMC is a good choice to model the flow around the micrometer level structures. In aerospace engineering and planetary science, the rarefied gas has a very long mean free path, surpassing the length of aerospace objects. In this case, DSMC is also a good tool to model such flows. More details of DSMC and calculations will be given in the following lessons. For further reading, please refer to the book by G.A. Bird. Besides the DSMC method, there is another way to approximate flows, that is the lattice approximation of flows. In the previously introduced particle-based approaches such as MD or DSMC, the particles can move continuously in a 3D space. And using statistical mechanics, the properties of particles can be sampled and ensemble averaged to get the mean property. However, in the lattice approximation, the movement of particles is restricted to the lattice points. In the lattice approximation, the particles have a unit mass and discrete momenta. The movement is a grid dependent. Because of this, the flow problem is greatly simplified. The lattice-Boltzmann method is built on lattice approximation of flow. The dynamic equation used here is the Boltzmann equation combined with the so-called BGK approximation. More details of the lattice-Boltzmann method and calculations will be given in further lessons. There are three basic physical processes included in the LB method: flow, collision, and boundary condition. The state quantity here is the particle density. In each iteration of the simulation, the particle density is locally recalculated. The figure here depicts a most simple case of a two-dimensional HPP lattice. The two collision cases are horizontal and vertical collision. In the calculation, the flow and collision are iterated The lattice Boltzmann method has many successful applications to study multi-phase flow, porous medium flow, complex fluid, amphifields, liquid crystals, polymers, and colloid solution. It is a simple and very efficient algorithm for complex geometries and parallel computing friendly. However, the statistical noise means it needs a long simulation for averaging. Because of the simple collision and flow mechanism, it is difficult to control the flow parameters. For further reading, please refer to the article of A.J. Wagner.